Yeah, good evening, everyone. So this is the last week. So this time in the last week, whatever the professor was covered was actually the abstract vector space. For the last 7 week, we were mainly dealing with the Rn only, like the transformation was in Rn and in a product, everything we were studying in Rn. So from this week, like only this week, we were dealing with the all kind of vector spaces, that is general definition of a vector space and what is inner product and so on. So I hope you might have understood the concept already. Anyhow, we will do the problems related to the general vector spaces, like other than Rn also we will do some more exercises. Okay, so first we will start with the one question where you need to check whether one space, like one given subset, is a subspace or not. Okay, first let us start with the Rn itself, then we will go to other spaces. So the first question is, which of the following are subspaces of Rn? And the first option, W equal to set of all alpha such that a1 greater than or equal to 0. Okay, let me write what is alpha. Where alpha is written as a1, a2, etc. an, and in Rn n greater than or equal to 3. So we are considering Rn with the n greater than or equal to 3, and the first space is given as set of all alpha where the first coordinate a1 is greater than or equal to 0. So can anyone tell whether this is a subspace of Rn or not? So what are, yeah.
I'm just thinking since this W is a set of alpha, where alpha is a tuple of n
Yes.
dimension, so it represents a vector in Rn.
Yes.
So, but is it forming a complete subspace that it will be right?
Yeah. What is the definition of subspace?
Uh,
Subspace
a
means,
space within a outer space which it can
yeah,
uh,
we can
okay.
say a vector, it itself is a vector space and it is a subset of some space. Here it is a subset of Rn. Obviously W is a subset of Rn. And if
Okay.
W itself is a vector space, W itself is a vector space means W should satisfy, there are some 8, 9 conditions, right? If all the conditions are satisfied, then W will be a vector space and it is a subset of Rn. So we will call it is a subspace. Fine.
Yeah.
Okay. Yeah. Now to check whether one subset is a subspace, we just need to check only two conditions. So one thing is, first of all, W is non-empty or not. At least that zero element. The thing is, you should check whether zero is there in W. If zero is not there in W, okay, W is not a subspace. First of all, we can conclude that. Okay. So first of all, whether zero is in the given W here.
No. A1, A2, where A is greater than equal to 0, it is there. Yeah.
Yeah, it is there. Only condition is for the first coordinate a1, it is greater than or equal to 0. So it can be 0 or any positive. So all other a2 etc. n can be anything. So it can be 0 also. So 0 belongs to W. Now, if two elements, the second condition is if two elements alpha, beta are in W, then alpha plus beta should also belongs to W. And the third condition is if alpha in W and C is a scalar, then C alpha belongs to W. So only these three conditions need to be checked. All the other conditions like commutativity, associativity, all those conditions will follow automatically. So to check the subspace condition, only these three is enough. Okay. Now you just check whether 2 and 3 are satisfied for this W or not, the given W.
Ma'am, the last one you said that if alpha belongs to W.
Mm.
then C times alpha, right?
Yeah. Yeah.
Okay, so C times alpha should also be belonging to W,
Yes.
right? Okay.
Okay, check whether the third condition is satisfied here or not.
So if we have alpha into tuple a1 comma a2 till an, uh, so it will be alpha a1 like if you multiply a scalar to a tuple, it will
Yes.
become
Like with each coordinate, it will be multiplied.
yes, yeah,
CA1, CA2, etc. CAN. So
yeah.
if that C alpha belongs to W, what should be the first coordinate? CA1 should be greater than or equal to 0. Correct?
C a1, yeah.
Yeah.
C a1 should be greater than equal to 0, yes.
Will it be true always for any scalar C?
Yes.
Yes?
Yeah, because C is a scalar, and anything scalar into a greater than equal to 0 will be again greater than equal to 0, right?
Okay, can you tell some scalars like what is our field here? We are taking Rn over R, we
Yes.
can say real
Mm.
numbers.
Yes.
Okay, so what are all the scalars here? What are all the values C here?
C can be like any integer
Any
or
real number. Actually, field is real number R. Okay,
yes,
so
yeah,
C scalar means it is coming from the field R. So it can be
yeah,
any real number. Now, what
yeah,
about if C is a negative real number, say -1?
yeah. Then it will. So real numbers include. I'm not sure if real numbers
Yeah,
include negative.
real number means all like 0 and all the like numbers here and all the
Yeah.
numbers here.
So if even if C is negative, it will still be a real number, right?
Yeah, real number means the whole line will come. Complex means the whole plane will come.
Mm.
Okay, so
Okay.
for example, we can say if I am taking 1, 0, 0, etc. 0, it is an element in W. Okay, the condition is A1 greater than or equal to 0 is satisfied. Now, if I am multiplying, let C equal to -1. So, this is my alpha. So, C alpha will be -1, 0, etc. 0. So, this does not belongs to W, right? Okay.
This is a real, right? I mean, still it is real, correct?
No, no. What is the okay? If it belongs to W, what should be the condition? The first element should be greater than or equal to 0. Correct? First coordinate.
Okay, okay,
Okay.
okay,
Here it
okay.
is -1. If I am multiplying with a negative number, the first one becomes negative. So it is not a uh, vector
Oh,
space.
I got it now. Yeah,
Yeah.
I just thought A1 is greater than equal to 0. It's okay. I missed out that condition. Thank
Okay.
you.
So okay. Now one more question. We have the same vector space Rn. We need to check whether W equal to set of all alpha such that A1 plus 3A2 equal to A3. Okay, that means alpha means again A1, A2, A3 up to AN. Okay, here whether W is a subspace or not.
Um, you're taking the second condition, right, ma'am?
All
You're taking.
condition we need to check like it is non-empty or you need to check whether 0 is there in W first.
Okay. So this one you're saying alpha is such that it is a sum of even.
Yeah, this is like alpha is a1, a2, etc. an such that first coordinate plus 3 times second coordinate, sorry, 3 times second coordinate should be equal to third coordinate. So set a collection of all tuples which satisfy this condition. So we are collecting all such tuples, okay, and that is our W. So we need to check whether W is a subspace. First we need to check W contains 0, 0 means 0, 0, n tuple 0. Whether 0 is there in W. That means whether 0 satisfy this condition or not. That is the question. 0 means 0, 0, etc. 0.
So this is not in W because A1 has to be greater than 0 for W.
No, no, no. That is the first question. The second question is this one. W equal to set of all alpha which satisfy the condition A1 plus 3A2 equal to A3.
Okay.
Okay, that is another set which is not a subspace we proved. Whatever I
Hmm.
have done the first one A. Okay. Now we
Okay.
are going with another set. Say let me write W1. Okay.
Okay.
So this W1, in this W1 whether 0 belongs or not. So what is the A1 here? This is, suppose this is A1 etc. AN 0. Instead of 0 I am writing A1 etc. AN. So what is A1 here?
It satisfies the
Sorry,
condition.
sorry, can you repeat it?
Ma'am, it satisfy
Yeah,
the
it
condition.
satisfies the condition because A1 is 0 here and A2 is also 0 here, which is equal to A3. A3 is also 0. So 0 belongs to this one. So W1 is a non-empty set because 0 belongs to W1. Now the next thing we need to check is if two elements belongs to W1, whether the sum belongs to W1 or not. Okay, can anyone tell very quickly? Suppose I am taking two elements A1, A2, etc. AN and B1, B2, etc. BN belongs to W1. It belongs to W1 means it should satisfy which condition?
That
This,
means A1 plus B1, A2 plus B2, and A3 plus B3 must satisfy A1 plus जो हमने condition लिखी हुई है A1 plus 3A2 is equals to A3.
yes, that means the sum A1, A2, etc. AN plus B1, B2, etc. BN that should satisfy this condition. So here A1, etc. AN belongs to W1 means A1 plus 3A2 equal to A3. Similarly, B1 plus 3B2 equal to B3. Okay. Now, what is the sum of these two? A1, A2, etc. AN plus B1 etc. Bn is A1 plus B1 to An plus Bn. So if this belongs to W, what does this means? First coordinate is A1 plus B1. A1 plus B1 plus, so here the condition is first coordinate plus 3 times second coordinate. 3 times second coordinate is A2 plus B2. Okay, it should be equal to the third coordinate. Here the third coordinate will be A3 plus B3. Okay, is this true? If this is satisfied, we can say it belongs to this element belongs to W. Is this one true?
If we add the above two equations, A1 plus 3A1, A2 is equals to A3, and B1 plus
Hmm.
3, B2 is equals to B3, then we get the same.
Yeah, we will get, if we are splitting it like this, A1 plus 3A2 plus B1 plus 3B2. So from this
Yes.
equation star, what we will get, this is equal to A3 plus B3. That is what we want. Okay. So if we are taking the sum of two elements in W1, the sum also belongs to W1. Now the third condition is if we are taking one element A1 etc. AN and multiplying with the C. That means we will get the CA1, CA2 etc. CAN. Whether this belongs to W or not. Can anyone say? So only thing is we need to check first coordinate here, first coordinate plus 3 times second coordinate equal to third coordinate or not. What is the first coordinate in this one? CA1. Okay, plus 3 times second coordinate. What we were having a1 plus 3 times a2 equal to a3. So here CA1 plus 3 times CA2. If I am taking the C outside, what I will get? A1 plus 3a2. Since a1 etc. an belongs to W, this condition is satisfied. That is, this condition is satisfied. So we can substitute CA3. Okay, so this is the third coordinate. This one is the third coordinate of C alpha. Okay, so we have proved the three conditions. First one is W1 is non-empty, and the second one is if we are taking two elements from W1, we proved the sum of the element is also in W1. And the third condition, we proved if an element is in W1, then the scalar multiple of that element is again in W1. Okay, is that fine for everyone? So this is just a calculation. You can just do it yourself, then you will understand more. Okay, yeah. Now one more quick question. I am giving another subset W3, again a subset of Rn. Set of all a1, a2, etc. an such that a1, a2 equal to 0. Okay, just leave about the W1, W2, everything. So this is a new subset to W3, which is a subset of Rn. Is W3 is a vector space or not? Or subspace or not? What is the first condition?
It must not be phi. That
Yeah.
means 0, 0 satisfies this equation.
Okay, whether 0 belongs to W3?
Yes.
Yes, because the condition 0, 0, etc. 0 belongs to W3. Because here A1 is 0 and A2 is 0. If this is our A1, A2, etc. A1 is 0, A2 is 0. So A1, A2 equal to 0. So this condition is satisfied. So this 0, 0, 0 belongs to W3. Now, if I am taking two elements from W3, will the
Um,
sum belongs to W3 or not?
Ma'am, this 0 belongs to W. Like, can you please elaborate on this one? Because
Okay.
say we have a condition that a1, a2 is equal to 0. So we are saying a1, a2 can be 0 if both a1 and a2 are 0, right? So,
A1 into A2 equal to 0, not A1 comma A2. A1
yes, yes.
product A2. Okay.
Yeah. So this means that 0 is a tuple in this subspace, uh, right? So,
Yes, yes.
okay. So, 0 being a tuple in the subspace, can you please explain, like, is it a mandatory condition for a subspace to be a subspace? Like, why is it like that?
No, for a subset to be a subspace, 0 should be there in that subset. Okay.
Okay.
If I
Yeah.
am taking some non-zero element, a collection of non-zero elements,
Mhm.
definitely it is not going to be a subspace. Whatever the condition are satisfied, if 0 is not there, then it is
Okay.
not a subspace.
Okay, that is one of the condition that zero
Yeah,
zero zero tuple should be a
it
part of.
should be there. Like
Okay.
here 0 is coming from Rn. Like what is the 0 in Rn? 0 0 tuple 0 0. Okay,
Yes. Yes.
okay, so that 0 should be there in the subspace.
Okay, then only we can call it a subspace
Yeah,
of
first
Rn.
condition is that, not just this one. Then we need to check that sum and scalar multiple also there in the subset.
Okay. Okay.
Okay, yeah.
Yeah.
Now what is our second condition? If two elements are there, whether the sum is also there in W3 or not? Can you think about that?
So alpha is equal to uh,
Okay, I will give you a hint. If two elements are there, it need not be true that sum is also in W3. Okay, that means I am taking an element A1 etc. AN belongs to W3 and B1 etc. Bn belongs to W3. Okay, so this belongs to W3 means this belongs to this set. That means first and second coordinate multiplication gives us 0. So here this gives A1 A2 equal to 0, and what will this give?
B1, B2 is equal to 0, second one.
B1 B2 equal to 0. Now my question is, can you find two elements like this? Okay, two elements A1 etc. and B1 etc. Bn such that this condition is satisfied. But if I am taking the sum A1 plus B1, A2 plus B2 etc. An plus Bn such that the product of first two coordinate, sorry, A2 plus B2 not equal to 0. Can you wisely choose such elements A and B?
So if A1, A2 is equal to 0 and B1, B2, then one of them has to be 0. Like A1
Yeah.
can be 1, 1, 0, and then continued by any real numbers.
Okay, suppose it is 0, 0 remaining.
Uh,
This belongs to W3. Okay, now what can you take as the second element?
that can be like 0, 1.
Yeah, of course, 0, 1.
Yeah.
0, 1 if I am taking, this also belongs to W3. Now what is the sum?
Sum is 1, 1,
Yeah,
which
so
is
1,
third.
1 remaining are 0. Does this belongs to W3?
No.
No.
Yeah.
Okay, so W3 is not a subspace.
Okay.
Okay, that's all. Okay, so this is actually coming from the Rn only. In the last week, we have studied about other subspace also, like other vector space also. So we will do some questions in other vector space. So one is, okay, in the videos you might have seen the set of all functions is a vector space, continuous functions. Okay, so the second question is, let V be the vector space of, okay, let me write real vector space. What does this mean, real vector space?
It's not complex.
Yeah, the underlying field is real, not complex. Like the field we can choose as C or R or anything like that. Okay. If we are choosing the field as complex, then the scalar multiple will include all the complex multiplication also. That means we can multiply a vector with the I also. Okay. But if we are choosing the field as real number, just multiply with the real numbers only. That's all. Okay.
Mhm.
Okay. So here we are taking all continuous function from R to R, real numbers to real number. Okay, not continuous function, just functions. So, which of the following are subspaces? Okay, first of all, a space of set of all functions from R to R is a vector space. That maybe you can verify. Okay, this is a vector space. You can verify later. So, what is the zero element here? Zero element of set of all function. What is the definition of zero element?
0, just because this is R to R, so wouldn't it be just 0?
No. What is the vector space here? Set of all function from R to R. So zero element is belongs to the space V, correct? So zero element is a function.
Okay.
Okay. So zero element is the zero function.
Okay.
0. That means 0 x equal to 0. This 0 denotes a function actually, the first 0. Okay, that means let me write it as some g from R to R such that g of x equal to 0 for all x in R. Okay, so obviously g belongs to this v, right? Because it is a function from R to R. And g maps every element to 0 element. So this g is called 0 function.
Okay.
Okay.
Okay, so any value of x, g is just 0. Okay.
Yeah, because now why g is a 0 function? If I am taking any function from v, what will be f plus g of x? This is f of x plus g of x. Since g of x is 0, this is equal to f of x. Correct? That means if I am adding with 0 element, I am getting the same element. F plus g is f only.
Mm.
Okay, f plus g equal to f. In the same way, we can say g plus f is also f. That is why we call the 0 function as the 0 element. If I am adding with another element, I am getting the same function. Correct? Okay, so this is the 0 element. Now I will give some subset of the v. Okay, v is the vector space here. Let me give the first w1 as set of all f such that f of x square equal to f of x whole square. Okay, that means the set of all, let me write it as, yeah,
Someone is
any doubt? Shilpa, any doubt?
मैम जो हम ये फंक्शंस ले रहे हैं, इज इट ए रैंडम चूजन फंक्शन या फिर कोई स्पेसिफिकली चूज करना पड़ता है?
Which functions v?
Like you have taken firstly a zero function, right? And then now you're choosing a f of x square is equals to f of x whole square.
No, no, no. What I was doing here is, I was just asking you a question. What is the 0 element? Like in Rn, what was the 0 element? The n tuple 0, 0, 0, right? In the same way,
Yeah.
what is the 0 element in the vector space? So we cannot just say 0 is the 0 element, because 0, the number 0 does not belongs to V, correct? V
Yes.
consists of all functions only. So the 0 element, 0 vector in V is the 0 function. Even if we are writing just 0, the real meaning of
Yeah.
0 is 0 function. So that is what I was doing in this first part. Now I am
Okay.
giving a subset. W1 is a subset that such that I
Okay.
am collecting all elements from V. V is set of all functions.
Oh.
Such that the function satisfy the condition f of x square equal to f of x whole square. Okay.
Mhm.
Now my question is, like there are many functions in W1. Okay. Now my question is whether W1 is a subspace or not. It is a subset of V. Okay. Now, how will we check whether it is a subspace or not? What was the conditions?
so does it have a zero function?
Yeah, 0 function is there or not. Okay, can
Mm.
anyone say whether 0 is there in W1 or not?
So f of 0 square is equal to f of
No.
so if take x is equal to
No, what
0,
is 0? 0 is the function. That means
yes,
instead of f, we should give 0, not instead of x. X
correct.
is varying in R, okay?
Yeah, got it. So f of x it should itself should be 0, right? So
Yeah,
if
that
f of x be
That means 0 belongs to W1. That is the question. So, if 0 belongs to W1, what should satisfy 0 means the function 0. Okay. That means 0 of x square. Like whatever I am writing 0 means 0 function here. 0 of x square should be 0 of x whole square. So, that is the condition here, right? Instead of f, now I have the 0 function. Okay. Is that okay for everyone?
ma'am, this is a continuous function f such that a function of x square is equal to function of x whole square, right?
Yeah,
So,
f need not be continuous also. We are taking v as the set of all functions from R to R. Like if
okay,
you are taking continuous also, there will be no problem. Okay.
okay. Uh, so, like you explained that a zero function is g of x is equal to 0, wherein the value of the function is 0 for all values of x. For
Yes.
so here, if we want to prove that this W1 set, does it contain such a function for a particular set of values of x, whether f will go to 0 or not, right?
So, okay, let me explain again. What is the zero function here? G of x equal to 0 for all x in R.
So
Okay.
here the function in question is f, right? So we want to prove whether f of x is equal to 0, right?
No, 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 no. What is the set W1? W1 means set of all functions. It is just f is just a notation.
Okay, okay.
Okay. G
So
can also be in W1. If I am taking
mhm,
some other function h, it can also be in W1. If h belongs to W1, I will say h of x square equal to h of x whole square. That's the difference.
okay.
F is just a notation. So my question is whether this G, zero function is G, I am denoting by G, okay? Whether this G belongs to W1 or not. If F belongs to W1, what is our condition? F of x square equal to F of x whole square. Okay. Now, if G belongs to W1, what should be the condition?
uh, g of x square is equal to g of
G
x
of
whole
x
square.
square equal to G of x whole square. Now, what is G of x square? What is this one?
G of x square. Uh, it will be 0
It will be
because
0 because G maps every element to 0, right? And what is
mhm,
G of x whole square?
that is also 0.
0. That means these two sides are equal.
Mhm.
So G belongs to this W1, right? Because G
Yes.
satisfies the given condition. So
Okay.
the zero function, I am usually zero function will notate by 0 only. Okay, so just to avoid confusion, I am taking it as G. So the zero function belongs to W1. Okay. Now what is the next question? Whether sum of the, if I am taking two functions, say f1, f2 in W1, whether f1 plus f2 belongs to W1. Okay. Can anyone think of that? Like if two functions are there, whether the sum belongs to W1 or not?
So that means f1 x square plus f2 x square is equal to, we want to check this, right? I mean, if these
Yeah.
are equal,
This implies f1 of x square equal to
square,
f1x whole square and f2 of x square equal to f2 of x whole square. Correct?
and
So,
the sum should belong to W1, right? Then only we can show that the sum belongs to, this is a sum is also belonging to W1, right?
hmm.
Okay.
Okay, now let me take f1 equal to f2 equal to f, where uh, f is defined as okay, f of x equal to 1 for all x. Okay, I am taking both the function f1 and f2 as the constant function f1. What is that? F
Constant
of x equal
horizontal.
to 1. Okay.
Mm,
Now, okay, let us check whether f1 plus f2. Okay, first of all, f1 belongs to w1, right? What is f1 of x square? I am taking any x square, f1 of x square equal to 1. This is
yes.
same as f1 of x whole square. The same way it is true for f2 also. Okay. Now, what about f1 plus f2 of x? What is f1 plus f2 of x? f1x plus f2 of x. This is 2, right? The constant function 2. Fine.
Yes.
Okay. Now, f1 plus f2 of x square. What is this?
X.
What is the function f1 plus f2? For any x, f1 plus f2 maps to 2, right? Constant function. Correct? So, what should be at x square? Like whatever the value x square, what should be this one?
So yeah, it will be 2
2 only,
because
right? Yeah, constant function.
mhm.
Now, what is uh, the other side is f1 plus f2 of x whole square. What is this side?
This is 2 we have already proved, so this is like 4, right?
This is 4 because f1 plus f2 of x is 2. 2 whole
Mm.
square we are taking, it is 4. So, what we are getting? Both sides are not equal.
Yeah.
Okay, so it will not belongs to the given space w1, w1 or w2, whatever. Correct?
Yes.
Yeah. So, so this is not a vector space. Is that
Mm.
okay for everyone? Okay. Shilpa, any doubt? Okay, I think.
That's okay.
Yeah. Now the second question is W2 is set of all f such that f of 0 equal to f of 1. Okay, only at two point 0 and 1, the value is given f of 0 equal to f of 1. So whether W2 is a vector space or subspace or not. First of all, what is our 0 function here? G, correct? Whether 0 function G belongs to W2 or not. This is my first question.
Mhm.
If G belongs to W2, then G should satisfy which condition?
Ma'am, this is f of 0 is equal to f of 1.
Yes, yes.
Okay, so yeah, it should satisfy g of 0 is equal to g of 1.
Yeah, G0 is 0 and G of 1 is also 0 for 0 function, right?
Yes.
So, G belongs to W2. 0 is there. Now, if two functions I am giving f1 and f2 belongs to W2, what we can say? f1 of 0 equal to f1 of 1 and f2 of 0 equal to f2 of 1. Now, what is the question? f1 plus f2 belongs to W2 or not? So, what should we check here?
We want to take f1 plus f2 uh, of 0,
Yeah,
that is equal to f1 plus f2 of 1.
it should be equal to f1 plus f2 of 1. So, okay.
Yeah.
What is f1 plus f2 of 0? f1 0 plus, okay, like this we can write. Okay,
Yeah.
separate. What is f1 0 from here? f1 of 1. And f2 of 0 is f2 of 1 from this condition. Fine. What
Yeah.
is this?
This is f1 plus f2 of 1.
Okay, so the condition is satisfied, right?
Yes.
Now the third condition is some CF of 0 should be equal to CF of 1. Correct?
Yeah.
What is CF of 0? Like CF of 0 is? For example, I
C1.
can take one only, f1 only. So the same f1, whatever I have taken here, the same f1 I am taking. Okay. So cf1 of 0 means c times f1 of 0. What
Yeah.
is this? C times f1 of 1. That is this one, right?
Yes.
Okay, so this condition also satisfied. So this W2 is a vector space. Okay. So in the
Yes.
same way, some two more questions are there, like the subset of a this function space, such that whether it is a vector space or not. Maybe I will just write the questions. If we have time at the end, we will do, or you can do it yourself. So it will be good exercise. Okay, just try all the example. Set of all f such that f of 3 equal to 1 plus f of minus 5 w3 and w4 equal to set of all f such that f of minus 1 equal to 0. Okay, I will give the answer also. This is not a vector space. This is a vector space. Okay, for not a vector space, only thing is you need to find some counter example or something, or just check whether 0 is there in W3 or not. 0 belongs to, that is the hint. Start with this. Okay, so these two questions you do yourself, as we have like different kind of questions. Okay, we have to cover that also. Okay, if we have time, we can do at the end. So the next question is, let V equal to, do you know what is M2 by 2 of R?
Uh, M is a complex matrix. Is
No, M2 by 2 of R means set of all matrices of order 2
okay.
whose entries are coming from real numbers. Set of all 2 by 2 real matrices. Okay, so if we are giving not equals m by n of c, what will be this? The same way, what will be this one?
This is a set of M by N matrix which belongs to which has all complex numbers.
Yeah, matrices with the complex entries. Like
Mhm.
the elements in the matrix are complex numbers. Okay. Okay. So we are taking this this V M2 by 2 R. You can verify V is a vector space. That is a very easy exercise. Verify V is a vector space. So for that you need to check the condition addition, scalar multiplication, and all the condition like commutativity, associativity, that existence of zero element unit, all those conditions listed in the class you have to check. Now again I am going for just subspace condition because we just need to verify only three conditions. So the first one is set of all, it is a 2 by 2 matrices, invertible matrices. Okay, this is a subset of M2 by 2 of R. And the second question is set of all non-invertible matrices. That means set of all 2 by 2 matrices which are not invertible. That's also a subset of R. Okay. Can anyone say whether it is A and B are subspace or not?
So invertible matrices uh, which are real 2 by 2 matrices
Hmm.
and we want to say whether it is forming which whether it's a vector space.
Yes. For example, what was our first condition to check a subspace?
Whether 0 is an element of the
Okay.
set.
First of all, whether 0 belongs to this A. What is 0 here?
Zero matrix.
Yeah, 0 matrix, obviously.
Mm.
0 element is a 0 matrix.
Yeah.
Whether this 0 belongs to the set A.
Yes, because it's a 2 by 2 real, so it can be 0 0 0 0.
No, no. What is A? A is set of all invertible matrices, which is a subset of M2 by 2 of R. I am asking about this one.
Ma'am, your pointer is not okay.
Wait. This is my W1 and this is my W2. Okay. Whether 0 belongs to, this is a subset of M2 by, now I just know it is a subset. I don't know whether subspace or not.
Yeah, so 0 will not, because invertible matrix will not have a 0 element. Yes.
Yes, 0 will not belongs to W1. Okay. Now, that is enough actually. But just for clarification, I will give, uh, for example, okay, 1001 is an invertible matrix plus minus 100 minus 1. That is also an invertible matrix. And sum is 0. This is not invertible. Okay. So
Yeah.
this belongs to W1. This belongs to W1. This does not belongs to W1. Okay. So the first condition 0 not in W1 is enough actually. If you just want clarification, you can do this also.
Okay.
Okay. Now what about B? 0 belongs to W2 or not?
Yes.
Because it
Yeah.
is a non-invertible matrix. So
Yeah.
0 belongs to W2. Now
Hmm.
we need to check the other two conditions. Can anyone say the other two conditions are satisfied or not? That means sum of two invertible matrices is invertible or not. Sorry,
Some of the
sum of two
non.
non-invertible matrices is non-invertible or not. That is the question.
Hmm.
Take some simple invertible matrix
Yeah.
such that it can be written as sum of two non-invertible matrices. Then we will have a counterexample, right? What is the symbol uh, non-invertible, sorry, invertible matrix
Can
identity?
take, we can take 1 1 1 1 also.
1111 is not invertible, right?
Yeah.
Okay, if we are taking 1111, then
Like similar matrices which where the determinant is 0. So like 2 2 2 2. Again, if we take, then sum will be 3 3 3 3, which is again not invertible.
okay, but this does not give any conclusion, right? What is this? This belongs to W2, this belongs to W2, and this belongs to W2.
Right. But we are not finding a contradiction. You're right.
Yeah.
That's We have to find a contradiction. Yeah.
So find two matrices such that this and this
Mm.
belongs to W2, but this
But
does not belongs to W2. That means this is a
non
invertible.
invertible matrix. Yeah.
Yeah. Okay, just take the invertible matrix as identity matrix.
Okay.
1001. Now, how can you write it as sum of two non-invertible matrix?
1000
Yeah,
plus 0001.
yeah. Here, this belongs to W2. This is also because these two are non-invertible, but it is invertible.
Mhm.
Okay, so it is also not a vector space. Okay, So
Hmm.
all invertible matrices is not vector space, non-invertible matrices also not vector space. So now I will give one example of a subspace of this M2 by 2 of R. For example, let me take M n by n of R. What is this? Set of all, I'm just generalizing the things, okay? We were doing in 2 by 2, n by n matrices. So set of all invertible and set of all non-invertible. So both of these set does not form a subspace. Now I am taking a space W3, set of all A such that A is symmetric. What does mean by symmetric? A matrix is symmetric.
Yeah. A is equal to A transpose.
Yeah, A equal to A transpose. And okay, let me take W. Okay, is W3 a subspace? First, let's go very quickly. 0 belongs to W3. Is it true? 0 matrix belongs to W3.
Yes, yes.
Yes, okay. Now, if A and B belongs to W3, we need to check A plus B belongs to W3 or not. So, we need to check A plus B transpose is A transpose plus B transpose.
Belongs to W.
This is A plus B. So, A plus B is also symmetric, right? And the third condition is CA. If A belongs to W3, what about CA? So we need to check CA transpose. That is C times A transpose. C means some constant. Constant
Yeah.
means it is multiplied with each of the entries in A. Okay. C times A transpose, C times A. So CA transpose is CA. So this is a vector space or a subspace. Hmm. Now
Yeah.
my question is, since it is a subspace, it itself is a vector space, what is the dimension of, we have seen the dimension concept in R3 and also here, what is the dimension of W3? That is my question. Okay. Before going to dimension of W3, anyone knows what is the dimension of Mn by n R? This itself is a vector space, correct? Set of all n by n matrices with real entries.
Yeah.
So
So dimension of this is n
n, y,
because it's a n by n real matrix, and the basis will have n elements in it.
what are all the n elements? Can you say?
Like 1 and n minus 1 zeros, like that, 1 1 in each
Okay.
element.
So
That
how
will
many elements you can form like that?
like n linearly independent set of these are like the base standard basis,
Okay.
right?
For example, let me take 2 by 2 matrix.
Hmm.
Okay. So what are all the elements in the basis?
0 1 1 0.
0, 1, 1, 0.
No, no, sorry. 0 0 0 1. 0 0 0 1.
Hmm.
Then one in at each vertex of this.
Okay.
So 0 0 0.
Like this. So
Yes.
how many elements are there in the basis? Now you tell.
Uh, Four of them.
4 elements. That means 2 square because there are 2 square entries in the matrix.
Okay.
So what is the dimension of Mn by Nr?
N square.
N square because there are n rows, n columns, so total n square. So at each position we can give one remaining 0. Like that we have n square uh, elements. So n square is the dimension of Mn by Nr. Okay. Now the question is, what is the dimension of W3? Okay. Now again, before going to this n by n, let us consider 2 by 2 symmetric matrices. In general, a matrix will be in the form A, B, C, D. So, what is A transpose?
ACBD.
A, C, B, D. Now, if it is symmetric, if A equal to A transpose, B should be equal to C, correct?
Yeah.
Yeah. So what is the general form of symmetric matrix?
A, C, C, D.
A, C, C, D. That means there are three variables, correct? A, C and D. So how many elements will be in the dimension, sorry, how many elements will be in the basis for the symmetric matrix? W3 is our symmetric matrices, right?
3. So it will be
Yeah.
like n square minus 1. I don't like
Okay.
it's 2
Let us
minus
see. So
4.
what will be the basis? 1, 0, 0, 0. The second element?
Uh, 0, 1,
Hmm.
0, and then 1 at the D position.
No, in
Uh,
like C means off diagonal entry CC. So for there it should be 1 1, right? Like this. Is that okay? First we are keeping C and D equal to 0. Instead of A, we are taking like 1. 1 0 0 0. Now A and D variable 0. So along the C only we will get some non-zero entries, say 1 1. Okay. Now A and C keeping 0. So that is how we will construct the basis. Like except one, all other variable we will keep 0, and one non-zero variable we will take as 1. Okay. So this forms basis. Basis of 2 by 2 symmetric matrices. Okay. Now let us go for 3 by 3 also. Then you will understand more clearly. Now 3 by 3 matrices means if I am having A here, B here, C here, what should be this entry and this entry?
B and C.
B and C. Okay, B and C. Now the diagonal, I can have any element, other element D. Okay, and if it is E, the next element here it is E. This is F. Okay, so how many variables are there?
6.
6 variables. So dimension of 3 by 3 symmetric matrices is 6. Okay, so what will be the basis? Basis, yeah, you can find the basis. Find basis yourself. Okay,
Hmm.
what are all the 6 elements? Find it. Now, are you getting any idea for how it will be for 4 by 4 matrices and in general for n by n matrices? But here you can see along the diagonal it is ADF. Okay, so just above the diagonal it is BE and just below also BE. Here it is C. So the diagonal and an upper portion or a lower portion, that only we need to be considered. Okay, see here all this portion if I am considering, here everything is distinct variables. Okay, A, B, C, D, E, F. But here in the below portion, the things are repeating. Whatever B is above, that B only coming here. Okay, so the variables are along the diagonal and upper portion. Correct? So
Yes.
for n by n matrix, for n by n,
Like n is in the diagonal, then n minus 1, and
yeah,
so it's from 1
here
to
we will have n variables along diagonal. Here we will have
n,
n minus 1.
yeah,
Finally we will have 1.
1
Okay,
plus
so how
n
many
and
variable will be 1 plus 2 plus etc. n?
n, yeah. So
Okay,
n into n plus 1 by 2.
n into n plus 1 by 2. So this is the dimension of n by n symmetric matrices. It's clear for everyone? Okay. Now,
Yes.
okay, sorry, W4 is set of all A such that A equal to minus A transpose. What is this?
Skew symmetric.
Skew symmetric matrices. Okay. So can you do it yourself for W for the like this? What are all the variables where at what all position it will come and what will be the dimension of W4? Can you do it yourself? It is just a same kind of things for symmetric matrices. Just see how it will be arranged. For symmetric means we are taking 2 1 and 1 2 equal. In the same way, what should come for skew symmetric matrices? If here it is 1, suppose here is some element, here some element, here if here it is 1, it should be minus 1, right? So if in 2 1 position it is minus 1, then 1 2 position it would be minus of that one. And what should come in the diagonal? So can you check it yourself or should I do?
Uh,
Yeah, if you want to do we can do, but it's, yeah, same repetition only, we can do very quickly if you want. Okay, then I'll do very quickly. So if I am taking a skew symmetric matrix, for example, A should be equal to minus A transpose. So what should be the diagonal element, diagonal entries?
0.
Yeah, it should be 0 because if I am having a non-zero element here, okay, say A, and its transpose also, okay, this is my A. In A transpose also, that entry will come A only. A, some star, star, star like this. So this A should be equal to minus A transpose means small a should be equal to minus A. That implies A equal to 0. In the same way, all the diagonal elements are 0. Diagonals are 0. So in general, let us do for n by n. So here along diagonal, we got everything 0. Now if I have A here, what should be the element here?
Minus A.
Yeah, correct. Minus A. Then, okay. My voice is echoing. Okay, fine. So, corresponding to this element, we will have one basis element. 0, 1, 1, everything is 0. Everything else is 0. Okay.
Mm-hmm.
In the same way, corresponding to all elements above this diagonal, I will have some negative elements here because A equal to minus A transpose. Okay.
Ma'am, the one element, one matrix which you told is 1 1. Wouldn't it be 1 minus 1?
Which one?
On the right side,
Yeah, yeah, sorry. It is minus 1.
okay.
That is the basis element. Yeah, sorry.
Mm.
So, in the same way, corresponding to all elements along this second diagonal, okay, we will have some 1 here minus 1 in the respective place. Okay, so uh, in the symmetry case, we had diagonal also, diagonal, above diagonal 1, like that up to 1. Okay, but in skew symmetric, along diagonal, we got everything 0. And all others are the same kind of repeating like symmetric. You can do for 2 by 2, 3 by 3 like that.
Like
So
n
here
by
we
1
will get n minus 1.
minus
From
1.
here n minus 2 up to 1 we will get.
Okay.
Okay. So
Mm.
total variables, how many it will be? N minus 1 plus n minus 2 plus etc. plus 1. Okay, 1 plus etc. n minus 1 means n minus 1 into n by 2. Okay. The other one was n into n plus 1 by 2. This is n into n minus 1 by 2.
मैम नेगेटिव एलिमेंट्स को अलग काउंट करना है या फिर सिर्फ पॉजिटिव वंस आर सफिशिएंट टू काउंट?
Sorry, can you talk in English?
Ma'am, like we have taken a and minus a, so we have to count a separately and minus a series separately.
No. Because if you are taking an element, yeah, can you mute now for now? Yeah. If I am taking an element A, then the corresponding negative, if I am taking 1, then minus 1 should be there, not minus 2. So that minus 1 is determined by this 1. Whatever I am taking, its negative part should be there in the like respective part. So we don't need to count the down part. This part we don't need to count. This above part, how many variables are there? The same kind of, if it is A, here it is B, it should be minus B. Okay, the exact negative part is there. So only one time is counted. That means above portion.
Okay, ma'am. Thank you.
Okay, so that is how we can find the dimension. Okay, you can just verify. Earlier it was n into n plus 1 by 2. Here it was n into n minus 1 by 2. Just add this. Okay, you just check what you will get after adding this.
Actually, ma'am, the you have drawn like one element of the basis. The second element will make it like super clear if there is any doubt, because the second element would be like the third element there in the basis being like 0, 0, 1, and then from the top 0, 0, 1 in the column, a minus 1,
Yeah,
and then everything else is 0,
yes,
right? So like this minus 1 along the diagonal, there will be like n minus 1 sets, and then like that, if we go proceed towards the vertex of the matrix, it will keep on adding like you added. Yeah.
okay, I didn't get you actually what you
No,
are.
I was just trying to confirm if this is the basis elements, like so each basis element will have minus 1, 1, minus 1, 1, like
Yeah, like
that.
that only.
It will keep on. Okay.
Yeah, that is the standard basis. Like you can find
Okay.
other basis also. This we
Mm.
will use as the standard basis.
Okay. So the
Okay.
last one in this set would be at the extreme vertices, there will be 1 minus 1, right? That
Yeah,
would
here it will be. So here it will be some 1
everything.
minus 1 like this. Here it will be 0 like this. All
Oh,
others are 0. Something like this it will come.
like this is the only diagonal one. Like say if we continue this progression, then it would go to the right top 1, and then left bottom minus 1, right?
Okay, you are saying like here 1, here minus 1 like this.
Yes, yes, yeah.
Yeah, like
That
this
is,
it will come. After that,
mm,
whole the upper diagonal part I need to consider, right? So this will come at the end, right? See,
okay.
this is means I covered up to first row only. Now I will
Yes.
go to second row 1 minus 1 like that.
Yeah,
So
yeah.
up to this I need to go.
Yeah. So
Okay.
there is one which we have in the sum at the below this matrix, the plus one, right? So this one, because we are saying that along the diagonal, the sub-diagonal elements are combination of n minus one terms, right?
Yeah.
Then
Because
this one, the single one, which is only one, which one is that one?
okay. Here along diagonal we got 0.
Yes.
Okay, so along diagonal we have n elements.
Yes.
Okay, after this how many elements are here?
N
Adjust
minus one.
n minus 1 elements. So
So this
uh,
will form n minus one
n
basis.
minus 1, because first I will have here 1, here
One
minus 1, all other
minus one.
0. Next
Yeah.
here it will 0. Next here it will be 1, here it will be
One.
minus 1,
Mm.
like that. Okay,
So
as you
the
said, so it will be the
single.
last element. Yeah, yeah, correct.
Oh, okay,
So
okay.
then we will go next. So that last one correspond to this element actually. Sorry. Yeah.
I see. Okay,
Yeah.
thank you.
Okay. Okay, then let's go to the next one. Okay. Now the question is, let W1, W2 are subspaces of a vector space V such that W1 plus W2 equal to V. So W1 plus W2 means collection of all. What does this mean? Set of all W1 plus W2 such that W1 in W1 and W2 in W2. That means we are adding all the possible combination from W1 and W2. Okay. And the given condition is the intersection is just 0. Now the question is prove that for each alpha in V there exists unique alpha 1 in W1, alpha 2 in W2 such that alpha equal to alpha 1 plus alpha 2. That means there is only one way to write this alpha as alpha 1 plus alpha 2. Is that okay? Question is fine?
Ma'am, can you please clarify this question?
Yeah, I am taking two subspaces of a vector space such that if I am adding these two spaces, adding means I am taking all the elements from W1 adding with W2. The same way taking all elements from W2 adding with the W1 means all the possible combination I will take. Okay, so that sum is equal to V and the intersection of these two spaces W1 and W2, it is just 0 element. That means 0 subspace. This is the given condition. Okay, these two. Now, for each alpha, I am taking any element from the vector space V. We need to prove that there exists a unique way of representing alpha as alpha 1 plus alpha 2, where alpha 1 coming from W1 and alpha 2 coming from W2. Okay, that means if I am writing alpha as alpha 1 plus alpha 2 and in another way I am writing beta 1 plus beta 2. This is not possible. If I am able to write this, alpha 1 should be equal to beta 1 and alpha 2 should be equal to beta 2. Is that fine?
So we are saying that, so just paraphrasing so that I get more clarity.
Yeah.
So alpha 1 and alpha 2 belong to the subspaces W1, W2,
Hmm.
and we want to prove that alpha, which is a which is an element of vector space V, also contains V alpha is equal to alpha 1 plus alpha 2. Is that what we are saying?
Yeah, okay. Let me write. Alpha is a element of V, right? What is
Yeah.
V? From given condition, V is W1 plus W2. Is that
Yes.
okay? Now,
Yes.
uh, W1 alpha belongs to W1 plus W2 means obviously I can write it as some alpha 1 plus alpha 2 where alpha
Correct.
1 belongs to W1 and alpha 2 belongs to W2. This is very clear
Yes.
part. Okay.
Yes. Yes.
Now the
Mm.
main point is to find the uniqueness. That means I can write it only in this way.
Okay.
Okay. Like for
Mm.
example, I can write 5 as 4 plus 1 and 2 plus 3. So this is not unique way. I can write 5 in two ways, right?
Yes. Yes. Yeah.
But if I am saying I can write in some sense 5 is 4 plus 1 only. I cannot write in any other way. Okay. That uniqueness, that is what I want to prove here. This alpha I can write only in alpha 1 plus alpha 2. Like only one way I can write. Okay.
Yeah.
Yeah. Now I am supposing alpha I can write alpha 1 plus alpha 2 and alpha I can write beta 1 plus beta 2. I am supposing I can write in two ways.
Mhm.
Okay. So either we should get a contradiction. If I am writing, some problem will come. Okay.
Mm.
Otherwise I should be able to prove this alpha 1 equal to beta 1 and alpha 2 equal to beta 2. Correct? Then also that is a unique expression.
Yes.
Okay, so we will prove this, we will get the second condition. That means if I am writing in two ways, I will get actually both are same. That is alpha 1 is beta 1, alpha 2 is beta 2. Okay, now alpha is alpha 1 plus alpha 2 and alpha is beta 1 plus beta 2. In this two way I am writing. Okay, now What is 1 minus 2?
Alpha 1 minus beta 1.
Plus alpha 2 minus beta 2. Correct?
Yeah. Mhm.
Now, alpha 1 minus beta 1 equal to minus of alpha 2 minus beta 2. Okay. Here, alpha 1 beta 1 belongs to W1. Alpha 2 beta 2 belongs to W2. This is fine, right? Because I am writing is W1 plus W2. Okay.
Yeah.
Now, from this equation, where does alpha 1 minus beta 1 belongs? In which subspace?
Ma'am,
Yeah.
if alpha 1 beta 1 belongs to W1, then our alpha must be alpha 1 plus beta 1 in a first equation, and alpha is equals to alpha 2 plus beta 2 in second equation.
Sorry. Can you repeat?
Actually, you have taken alpha 1 beta 1 belongs to the W1, right?
Yeah.
And alpha is a combination of W1 and plus W2,
Yes.
right?
Yes.
So uh, then you have taken alphas in a one equation and betas in a second equation.
No. What I am writing is this alpha 1. Okay, this alpha 1 belongs to W1 and this alpha 2 belongs to W2. That is alpha 1 plus alpha 2. Alpha is in that form. In the same way, alpha is beta 1 plus beta 2. Beta 1 is in W1 where beta 2 is in W2.
Okay, ma'am. Okay,
Okay.
done.
Yeah, this I have written like this, so that is why you got
Yeah,
confused.
that's why. Yes, that's why
Okay.
I'm confused. Sorry.
Now, alpha 1 minus beta 1 is, yeah, sorry, can you mute? Yeah. Alpha 1 minus beta 1 is minus alpha 2 minus beta 2. Now, where does alpha 1 minus beta 1 belongs? Which space?
W1.
Yeah, W1.
Uh,
Sorry. Belongs to W1. So, alpha 1 minus beta 1 is minus alpha 2 minus beta 2. Correct? So, minus alpha 2 minus beta 2 belongs to W1. Correct?
yes,
That,
because both are equal.
yeah, both are equal. If minus belongs means the negative portion also should belongs to W1 since W1 is a subspace.
Yes.
Yeah. Now in the same way, from here, from star, I can say, not from star, since alpha 2 or beta 2 are in W2, alpha 2 minus beta 2 in W2, right? And what is alpha 2 minus beta 2? It is negative of alpha 1 minus beta 1 from star. So, I can say alpha 1 minus beta 1 also belongs to W2. The same way I am writing. Okay. So, what I got?
Yes.
1 is this and 2 is this. From 1 and 2, I will get alpha 1 minus beta 1 belongs to W1 intersection W2. It belongs to W1, it belongs to W2. So, its intersection is just 0. So, what should be alpha 1 minus beta 1?
It is equals to 0.
Yeah, it is 0. That means alpha 1 equal to beta 1. The same way, I can say alpha 2 minus beta 2. Here I got in W2 and W1 belongs to W1 intersection W2, which is just 0 element. That means alpha 2 equal to beta 2. So, we started with the two expression. Okay, here. So, what we got, both the expression are actually same. Even if I am trying to write it in two way, I am finally getting both are same. So, there is a unique expression.
Can you please explain the last part where we have got the zero set?
Yeah, that
One.
is my condition. See, the condition was W1 plus W2 equal to V and W1 intersection W2 equal to 0.
Okay.
Okay, so I got alpha 1 minus beta 1 belongs to W1 intersection W2. That is 0.
So 1 and 2 equations, how are we like deriving from 1 and 2 that W1 intersection W2 is equal to 0?
Not
Because
from 1 and 2. Okay, let me
both are
just.
same, is that's why?
No, no. What I am getting is alpha 1 minus beta 1 belongs to W1. Alpha 1 minus beta 1 belongs to W2. That is okay, right?
Yes.
Yeah. So it belongs to W1 and W2 means it belongs to the intersection of W1 and W2. Okay. This is okay, right? This much.
No, ma'am, this statement is not very clear. Please can you?
No, no. What does this say? Says alpha 1 minus beta 1 belongs to W1.
Yes.
And what does this say? Is alpha 1 minus beta 1 belongs to W2.
Yes, yes. So it belongs to both the
Mm.
spaces.
Both space means its intersection also. In its intersection it belongs, right?
Okay.
Okay. And from question, what is that? W1 plus W2 is V and W1 intersection W2 is 0. That is given condition in question.
Mhm. So
Okay.
this means that there is no intersection, but we are getting something which is in the intersection.
Yeah. So in intersection only 0 element is there. So we are getting an element in the intersection. So it should
Oh,
be equal to 0, right?
okay, okay.
Yeah.
I got it now. Now I got it. Yeah. So because it is contradicting the initial the condition, and therefore alpha one
Actually, it
must.
is not contradicting. What we are getting is both this expression. See, whatever the expression here, this alpha 1 equal to beta 1, this alpha 2 equal to beta 2. That is what we are getting, right? So only one way I can write. Even if I am trying to write in different way, I am getting these expressions are actually equal. Alpha 1, beta 1 same, alpha 2, beta 2 same. That is what we got. Correct?
Mm-hmm. Yeah.
Okay. So we proved it. Fine. Okay. Now, okay, let me do one question from inner product. Okay, V is set of all M 2 by 2 of R. Okay, I'm defining an inner. I don't know whether it is an inner product or not. My question is define AB equal to determinant of AB. So my question is whether this is an inner product or not. Okay, so in the real case, we have just seen the dot product only. So other than dot product, we can have many inner product actually. Okay, so many inner product means it is a function which satisfies some condition. We have seen three conditions. Okay, so only thing is whether this satisfies the three condition or not. Okay, so do you remember what are all the condition?
Yeah, ma'am. The first one is that u dot v is equal to v dot u. And then there is u plus v dot w is equal to uw plus vw. And the third one is c of u is equal to c of u dot u. C of u dot u is equal to c of u dot u. But ma'am, I didn't get the question. This define a dot b is equal to determinant of ab. Is this
Okay,
like what is the significance of the statement?
what does the inner, okay, before giving these three condition, inner
Yeah,
product, what is inner product? Inner product is actually a function,
yeah.
correct? Inner
Mm-hmm.
product means some function. Instead of function, I am writing this notation. Two elements will be here, one element will be there, here one element will be there. Okay, this is a function from vector space to the field R or C, wherever, like V is in some field, either in R or C, something like this, right? So inner product is actually a function from V to R such
Mm-hmm.
that if I am giving two x and y here, it is going to some element star in R. That is
Oh,
what we were doing dot product. We will take the coordinate choice multiplication. So it is a from Rn to R, correct?
Yeah.
Sorry, not V, V cross V. Okay, two elements we will take. This is one element, this is one element. So from V cross V to R. Okay?
Okay.
Okay.
So this define which we have done is like A and B are two elements of V.
Yeah, now our V is
Mhm.
M2 by 2 of R. Okay. Now I am taking two elements A, B in V. What is A and B matrices? Correct?
Yeah.
And I am defining the function AB. Okay, I'm just defining a function. I'm not saying it is an inner product. Determinant of AB. This is an element of R, right? So it is a well defined. In terms of like inner product, what we are saying, it should be from V cross V to R. So this is belongs to M2 by 2 of R,
I
and this,
got it now. Yeah,
yeah,
I got
M2
it.
by 2 of R, and it
It is
is going to some real
yeah.
number.
Okay, I got it. Yeah.
Okay,
You want
now,
to check whether this definition satisfies the inner product or not.
yeah, now the all the conditions we need to
Yeah.
check. So
Okay.
one condition was, first condition was actually V dot V greater than or equal to 0, and VV equal to 0 if and only if V equal to 0. That one is one condition, right?
Yeah.
Yeah, this is the first condition actually. We should check this one. Now, can you take some metrics, okay, A and B, such that if I am doing AB, what is AB? Determinant of AB. If it is an inner product, it should be greater than or equal to 0. Correct?
Yeah.
Yeah. So, my question is, can you find two matrices from like two by two matrices such that this condition is not satisfied?
So determinant of A into determinant of B, can we do the distribution here?
Sorry, can you repeat?
No, like we have determinant of AB. So
Hmm.
can we do distributive over AB of the determinant?
Yeah, determinant of AB you can do.
Okay.
Yeah.
So if it has to be greater than
Okay,
equal to
one is this, otherwise you can say what is this determinant of, what is AA? Oh, sorry, it should be determinant of AA, right? Sorry.
yes. Okay.
It should be greater than or equal to 0. One is this one. Either try to find matrix such that like this, or if it is 0, A should be equal to 0, right? Means A is a 0 matrix. That is, this condition says.
So if we want to disprove this, we have to find an A such that there is some negative determinant. Then only we can disprove it.
Yeah, only that you can prove, whether that one or this one also you can prove. Any of this you can try to prove, either this or this. Like find two matrix, not two matrix, one matrix A such that determinant of A equal to 0, but A is non-zero.
Mhm.
That will be easy. Like first one will also you will get. I think you will get first also. But second it will be easy. Like take some matrix. That means determinant of A equal to 0, but A is non-zero. That is easy, right?
I'm thinking. Uh, for you it is easy, but
Okay,
yeah.
okay. Fine.
Uh,
Okay, one more thing. What we want to find is a matrix whose determinant is 0, but A is non-zero. That means a singular matrix, right?
yes, a singular matrix.
Will it work if it is A?
This is not singular.
Yeah, its determinant is non-zero. Now,
So,
what about this one?
yes. So determinant of A is 0,
Okay, determinant of A equal to 0,
but
but
A
A
is not
is
A.
non-zero. But this should be in the form A into A. I have just written one matrix.
Mhm.
Now, my question is, how can I write it as product of two matrices? I mean, product of same matrix.
Ma'am, determinant of A into A is equal to determinant of A into determinant of A, right?
Yes.
So if just we take one determinant, that is enough, right?
So, okay. So, how we will start A with any matrix? Yeah, A I can take any matrix, non-zero matrix such that determinant of A equal to 0. That is what you are saying, right?
Yes.
Yeah. Then obviously determinant of A equal to 0
Yeah.
with A non-zero. Yeah, that is enough. Okay, the example I was giving was A equal to 1 0 0 0. If you want, you can just note this. So A will also be, if multiplying A with A again, it will again be 0. So determinant of A is 0, but A is not 0.
Mm-hmm.
So determinant is the function we have defined here is not an inner product.
Mm-hmm.
Okay. Now again I can give uh, second question is AB equal to trace of the trace of AB. Do you know what is trace?
Yeah, the sum of the
Yeah,
diagonal.
sum of diagonal entries. So just check this is an inner product or not. Okay, can you do it yourself? The same procedure, it will not be an inner product. For that, you need to find some sufficient counter examples. That's all. Okay?
Mm-hmm.
Yeah. Okay. Now we will do some. Let V be an inner product space. Inner product space means first of all it is a vector space and it has some inner product on it. Okay.
Yeah.
With the inner product. So first question is show that 0 beta equal to 0 for all beta in V. We don't know what is inner product. Like inner product we can define in various ways as I told. Okay. The only condition is it has to satisfy the given 3 4 condition. So we are not saying in the question what is the inner product. It is some inner product. So just using the three conditions we already have, we should be able to prove 0 beta equal to 0 for all beta in V. That means 0 is the 0 vector here. Okay. And if alpha beta equal to 0 for all beta in V, then prove that alpha equal to 0. Okay. Leave second one now. Just we can see first one. Can you say why 0 beta equal to 0 or always? Now, what is my 0 beta here? This 0 is my vector, right? I am defining the inner product from V cross V to R. Okay. So, this 0 and this beta are vectors. And what is this 0? Is this a vector or scalar?
Scalar.
Yeah, it is scalar. So, if we are defining to R, it is the real number R. Correct?
Mm-hmm.
Yeah. So, the thing is we need to prove this vector 0 inner product with beta for any beta should be equal to 0. This is what we want to prove.
Yeah, but I didn't get the question completely, but we can. I will try to understand. Like, so we are saying that this is a given definition of the inner product. Is that what we are saying?
No, no. What we are saying is there is no well defined, like inner product means dot product is an inner product, correct?
Yes, yes,
Other
yeah.
than that, in real space, I can have another inner product also. Here,
Yes.
they are not specifying what is the inner product. They are just saying it is an inner product. This function is an inner product. That means
Okay.
it is satisfy the four condition we have, right? It should be
Uh,
greater than zero, and that addition, constant multiplication, and all. So V
huh.
is an inner product space with an inner product.
Uh,
Some inner product is there.
Okay, I
So
got it. Yeah.
whatever the inner product, this
Mhm.
condition 0 beta equal to 0 should be true. That is what we want to prove.
Okay.
So we can just use the condition from inner product. That some three condition is the that only we can use to prove this. Now, okay, okay. Zero is a vector, correct? Can I write it as a scalar into some element? A vector, some like the C alpha we will write, right? Like alpha is a vector, C is a scalar.
Yes.
Okay. Now zero vector. Okay. How can I write it as some scalar into some vector? Like alpha is any vector I am taking. So what should be the scalar here?
0.
0. So
Yeah.
this 0 I am writing 0 times alpha beta. Now what I can do?
So now we can take 0 out.
Yeah, because we have the inner product property, that constant we can take out, right?
Hmm.
Now this 0. Earlier from here I cannot take because it was a scalar. Now it is 0 scalar into some vector alpha. Okay. Now the constant 0 is scalar, so I can take that 0 outside. 0 alpha beta. Correct?
Yeah.
So whatever the element alpha beta inner product I am getting, it is multiplying with 0 means it is 0. Okay.
Mm-hmm.
So we proved 0 beta equal to 0. So we are not even considering what is beta. This is true for all beta, right? Whatever beta. So that's all. We are just using one condition and just writing it in terms of like 0 into alpha. That's all. Is that fine?
Yeah.
Yeah.
So
Now the second condition is the given that alpha beta equal to 0 for all beta in V. Okay. Now what we want to prove that alpha equal to 0. Can you say how we can prove? Okay, I will give one hint. Instead of beta, for all beta it is true, take some particular beta. What is that particular beta? Some specific beta. Okay, let me take beta equal to alpha itself. What I will get? For all beta it is true. If I am taking beta is alpha, then also what should I
no,
get?
norm of alpha.
Yeah, alpha equal to 0. Okay, again, what was the condition in inner product? Alpha greater than or equal to 0 and alpha equal to 0 if and only if alpha equal to 0, right?
Mm-hmm.
So
Yeah.
this is equal to 0 if and only if alpha equal to 0. Is that fine? Okay, that is
Yes.
what we want to prove, right? Alpha beta equal to 0 for all beta in B. Yeah, that was the question. Prove that alpha equal to 0. We proved it. Okay?
Yes.
Yeah. So this is true for any inner product. Uh, okay. Now next question is, okay, function spaces. We have already gone through the functions, like v equal to c minus pi pi. What is this c minus pi pi?
It's a set of continuous functions uh, in over this minus pi to pi range.
Yeah,
Like,
functions on minus pi pi. That means function defined on minus pi pi, continuous function defined on minus pi pi, and uh, continuous. That's all. Okay.
and we use a space of all such functions.
Yeah, V is the space of all continuous function. The minus pi to pi. That is our vector space now. Okay. Now, okay, you might have seen this is infinite dimensional. Okay, let me leave that thing. I am taking a set S sine square x cos square x. Okay, is S linearly independent or dependent? So in Rn we have seen many examples like independence and dependence. So the condition to check the independence or dependence is same. Equate C1 alpha 1 plus etc. Cn alpha n equal to 0. If all Ci's are 0, then it is independent. If at
Hmm.
least one Ci is non-zero, it is dependent. So here also the same way we need to check. The only thing is we are coming from Rn to some other like abstractive vector spaces. That's all. Okay. So S is two elements from V. Whether S is linearly independent or dependent. How should we start?
Yeah, alpha sine square x plus beta cos square x.
Beta cos square x equal to 0. Okay. This is equal to 0 means it is equal to, it is true for all x, right?
Yeah.
That
Yeah.
means this is a function. Alpha sine square x plus beta sine cos square x is a function now. Okay.
Yes.
That function is 0 means it is a 0 function. That means at every x value it is 0.
Hmm.
Okay. Now,
In minus pi to pi.
yeah,
Right.
all x in minus pi pi.
Hmm.
Okay. Now, in particular, if I am taking x equal to 0, what I will get?
Sine beta is equal to 0.
Beta equal to 0. So, we got one value, one constant value, scalar value beta 0. Okay. Now, what is remaining? Alpha sine square x. Since beta is 0, alpha sine square x equal to 0, correct?
Yeah.
Okay. Now, alpha sine square x equal to 0. Now, can we conclude from here that alpha equal to 0?
Yeah.
Yeah, because sine square x is like a non-zero function. It is varying like waves. Okay. So either alpha equal to 0 or sine square x equal to 0. Then only the product will be 0. But sine square x is 0 means it should be 0 for all x. That is not true. It is non-zero, 0, everything it comes. So alpha should be 0. So we got beta is 0, alpha is 0. Okay. So S is linearly independent. Fine. Now let me take S1 equal to 1, 1 minus x square, 1 plus x square. Is this linearly independent or dependent?
Hmm.
Just try to add these three elements, then can you do something?
So we will get a constant if we add this.
Yeah. So
Uh,
then try to add some scalar multiples.
so if we take different scalar multiples, we will get some remaining
Okay.
x values, right?
I am
X square.
taking 1 minus x square plus 1 plus x square.
If everything is all the coefficients are 1, then the
Okay, 1 minus x square plus 1 plus x square plus 1. What we will get?
I will get 3.
3 we will get. So this 3 is actually, okay, now let me take this 3 to this LHS. That means 1 minus x square plus 1 plus x square plus minus 2. Okay, is this okay? That means what is this 1 minus x square plus 1 plus x square plus minus 2 times 1 equal to 0. Now what can you say? What did I write in the last sentence now?
Oh, so
Yeah.
I mean there are coefficients which are non-zero, right?
Yeah,
So there
non-zero, but the
coefficients.
linear combination is 0, right? So S1
Yes.
is
So S is dependent.
linearly dependent.
Yeah.
That's all. Like otherwise also you can just C1 1 plus C2 1 minus x square. Like that also you can do, but like just by looking itself, maybe it will be easy to do.
This
Okay.
is difficult for beginners, ma'am, because like just by looking and like the trick which you did, -2, bringing -2 there, that wouldn't, like, if you have to have a very good practice for that.
Yeah, it will be difficult, but it is better to understand these kind of things also.
Yes, yes,
Like
yeah.
doing all the calculation, it will take time. So maybe in the objective type and all, you may not be
Yes.
having too much time sometimes. So this kind of things, after doing elaborately, just try to understand this. If we can do something easy way, that is very
Mm.
helpful in objective type question. Otherwise, like otherwise the usual exam, okay, you have to write all the steps and all, and so practice like this also, it will be
Okay.
good. Yeah. Okay, now I will give one question. Okay, let U and V are subspace of R8. Okay, Rn where n is 8. Okay, and given that dimension of U is 3, dimension of W is 5, and U plus W is the whole space R8, then prove that U intersection W is 0. Okay, before approaching this question, I just want to know, do you know this result? Do you know this result?
No, ma'am.
Okay, then, okay, you can just note it down. It will be very helpful while finding the dimension of some subspace. Okay, so if V is a vector space and U and W are two subspaces, then this result hold. Dimension of U plus W will be equal to dimension of U plus dimension of W minus dimension of U intersection W. So that is why I have given this question. So this is just the application of this result. Okay, what is the U plus W here?
Oh, it's a 8 dimension.
Yeah, 8 dimension, and the dimension of U is given 3, dimension of W is given 5, and the dimension of U intersection W. So from this we can conclude dimension of U intersection W is 0. So 0 dimension means it should be 0 subspace, right? Equal to 0. So that only we need to prove. So it is just an application of result. That is why I just gave this question just to give you
Mm.
this result. Okay. Yeah. Now one question. Set of four polynomials of degree 3, 3 union zero polynomial or zero function. Okay, so is this a vector space?
Union, zero
Degree,
polynomial.
yeah, zero polynomial means the zero function itself, like all the elements are mapped to zero.
Okay.
And all polynomials of degree 3. Degree 3 means a3x cube plus like
Yeah.
a2x square, like that, where the cube coefficient of cube term is non-zero. Okay,
Mm,
that means we can say V is set of all a0 plus a1x plus a2x square plus a3x cube is such that a3 non-zero. That means cube term is there. That is degree 3. That is what I am saying by degree 3. Union 0. 0 means 0 polynomial. Is this a vector space?
So again, this we will start with the three conditions, like
Yeah. Of course,
whether
0 belongs to V, right? Because in the question itself it is given 0. Now
yes,
consider two elements in V, but its sum is not in V. Can you find such two elements? So sum is not in V means that cube term is going. That is what we are saying, right? A3 should be non-zero. But in the sum, A3 is becoming 0. Then only we can find a contradictory example. Correct?
okay, hmm,
So think like that. That means x cube term should cancel off if you are
yes,
adding.
it's negative, then it will cancel out. Yeah.
Yeah, if I am taking in one function I am taking x cube, the second function I should take minus x cube.
Mm.
Okay? Is that enough? If I am just taking x cube and minus x cube, if I am adding, I will get 0. It belongs to V. So just x cube is not enough. I should add some more terms with that.
Yeah.
For example, I can take x cube plus x square. It is in V. And minus x cube, it is in V, correct?
Yes,
Both
but
are
yes,
degree 3 polynomial. So if I am adding, so this is P1 of x and this is P2 of x belongs to V. So P1x plus P2 of x will be x square. Okay? But it does not belongs to V. So it is not a vector space.
yeah.
The next question is, prove that inner product of UV equal to norm U plus V square minus norm U minus V square by 4. Okay, you can do with me. So we should start from this side. Like, what is norm U plus V square?
Uh, square u plus v dot u plus v.
Yeah, U minus V square by 4. So this is U plus V, inner product U plus V, U plus V.
Yes,
Yeah. Then what is this one?
u
U
minus
minus
v.
V, U
Yes.
minus V by 4. Okay. So what will come next step?
Uh,
Okay, first of all, it should be V is a real vector space. For complex vector space, it will be, the result will not be true, I think. Okay, for complex, there is an analogous result which comes with I and all. Okay, imaginary I. So it is just a real vector space. Okay. Yeah. Now, what will be the next step?
We can do the distributive thing,
Yeah,
which is property.
distributive
Yeah.
property. So it will be uu plus uv plus vu plus vv minus, okay, this is the first term, u plus v inner product, and the second term is uu uh, minus uv minus vu plus vv divided by 4. Okay, so this uu will be cancelled and vv will be cancelled. So here uv and vu are there. Okay, is that same? uv and vu are equal
Yes.
because it is a real. That is why I am specifying real vector space. In case of complex, uv equal to vu conjugate.
Okay.
Okay,
Mm.
conjugate will come. So that is why in complex it will not be true. So what we will get, uv 4 times are there, correct? 4 times uv divided by 4, it is equal to uv. So this is just a calculation.
Yeah.
Yeah. Okay. Now I will very quickly do one question. V is the vector space of all polynomials Do you know differentiation operator? Usual differentiation, you know, right?
Differentiation, yes.
Yeah. So a1x plus square plus a3x cube. Okay. So V contains all the polynomials of this form, that is up to degree 3. Okay. It can be. Okay. What is the dimension of V here?
Dimension of V polynomials from R to R. So this is a one-dimensional.
Okay. This is our V. Sorry, V. Okay. Which set will generate V? How many variables are there in V? We can see as a0 plus a1x plus a2x square plus a3x cube. So how many free variables are there?
Only one variable.
No, there are a0, a1, a2, a3. 4 are there, right? What is this? This is actually a0 into 1 plus a1 into x plus a2 into x square plus a3 into x cube. Okay.
Yeah.
So if I am giving a1, a2, a3 0, then I will get only the uh, term corresponding to 1, that is constant. So all constant element belongs to V, correct? When a1, a2, a3 are 0, I will get all the constant elements. Now if I am giving a0, a2, a3 are 0, I will get all multiples of x. Okay, in the same way all multiples of x square, all multiples of x cube. Okay, I will just write very quickly this one. Actually the basis of V is 1 x x square x cube. So dimension of V is 4. So you just verify that this is the basis. So what should you do? You should prove that linearly independence and spanning property. That means the set, this set should satisfy linearly independent. It should be linearly independent and it should span whole space. Okay, just by looking you can see it is actually spanning, correct?
Yeah.
Yeah.
Because A1 plus like all the constants
Yeah, all
0.
the combinations gives the elements. So linearly independent also just try to prove. Otherwise you can just remember for now, I think. And
Okay.
now, okay, if we have up to power n, a naught plus a1 x plus etc. a n x power n. So if V is set of all elements like this, then what will be the dimension?
n plus 1.
Yeah, n plus 1. Dimension will be n plus 1. Okay. Okay, now coming back to this, the same D, a naught plus a1x plus a2x square plus a3x cube. Now define D from V to V such that D of a naught plus a1x plus D of a polynomial P of x is P dash x. Okay, that is differentiating one time. So what will become a naught plus a1x plus a2x square plus a3x cube? What will be this?
a1 plus a2x.
2a2x, right?
Oh yeah, 2a2x plus 3a3x square.
Yeah. Okay. Now, what is the matrix form of D with respect to the standard basis? Standard basis means 1x x square x cube. Okay. How will you write the matrix representation of D? Do you remember how to write that?
Is it like coefficients?
Yeah,
A,
coefficient. First
okay.
we will do operation D, like
Oh,
apply D
1.
to 1, then x square. Okay. What is D of 1?
Uh, a0 plus a1 plus a2 plus a3.
No, no, no. 1 means the constant 1. That means what is P of x here? P of x is constant 1.
Okay.
Okay.
Yeah.
Now what is D of 1? That is D of P of x. What is D of P of x? Derivative of P dash P of x. Correct?
Mm.
That is the
Yeah.
definition. What is
A1,
that?
a1 plus 2a2 plus 3a3.
No, no, no. P of x is constant 1. What is the
Oh,
derivative of constant?
0.
0.
Yeah.
Okay. So we will write 0 into 1 plus 0 into x plus 0 into x square plus 0 into x cube. So this is our first column of matrix.
Now I did not get what we are trying to do here. Like,
No, no.
can you,
What is the matrix representation
of uh, of the
of the operator representation of D? Okay. Before
okay.
that, this D I have defined from V to V, right? Okay. Okay. You
Hmm.
can prove it is a linear operator. This you should prove. Okay. In general, in Rn, if we have some uh, linear map, we know how to write the matrix representation. Correct? The
Hmm.
same way, here we have changed the vector space. Vector space is the polynomials of degree less than or equal to 3. Now,
Hmm.
D is linear. Okay, D I have defined. It is your duty to verify D is linear. Okay? That means, how we will prove D is linear? D of P plus Q should be equal to D of P plus D of Q. P and Q are two polynomials.
Yeah.
Okay?
Hmm.
Okay, that you verify later. The condition of linearity you verify. Okay, now if D is linear, we can have a matrix representation for D. Okay, instead of applying D into some function, we can do that matrix of D into that polynomial. Like D and the transformation D and the corresponding matrix D are interchangeably used. Okay. To find the matrix, first we need to find the value of D at the basis. We found d of 1. It is 0. Now d of x. What is d of x? That means derivative of the function x.
1.
Yeah, 1. How we will write 1 into 1 plus 0 into x plus 0 into x square plus 0 into x cube. Now, what is d of x square?
2x.
2x. 2x means 0 times constant, 2 times x, 0 times x square, 0 times x cube. D of x cube, 3x square, right? So constant term is not there, x term is not there, and x square term 3 times x square is there, and x cube term is not there. So we will write the matrix as first corresponding to 1, we got the coefficient 0, 0, 0, 0. That we will write as a column. Okay. Now corresponding to the second one x, we got 1, 0, 0, 0. That is our next column. And corresponding to x square, it is 0, 2, 0, 0. The coefficients 0, 2, 0, 0. And corresponding to x cube, we will get 0, 0, 3, 0. Okay, so it is not just for Rn, we can have this kind of matrix representation for any linear map from a vector space to some other vector space. Is that okay?
And we took a transpose of the, so we put, how did we construct this matrix? Like we took the first coefficients.
Yeah, first this is the way to construct, the standard way to construct the matrix. First we
Yes.
will take the, we will apply the linear transformation to the ordered basis. That means 1 x, x square, x cube we applied, right? And we got one value. D of 1 is 0. Now we will write 0 as the linear combination of the basis element. That is, we have written here 0 into 1, 0 into x, 0 into x square, 0 into x cube.
So this is 0 into 1. Okay, I was
Yeah.
just, okay.
So whatever the coefficient here 0, 0, 0, 0, that coefficient we will write it as the first column. Okay. Now we will do for x. We got the coefficient 1, 0, 0, 0. That is our second column. Now for x square we got 0, 2, 0, 0. That is our third column. And the last one is 0, 0, 3, 0. That is our last column. So this is the matrix corresponding to our linear transformation D. Okay. Yeah. Now actually, okay, you just try to do, if you are interested, if you try to do these questions. Is D11, is D12. Okay, you can, if you are interested, you can try these two questions. It is not so difficult. 1 and 1 2, you know the definition, you just apply the definition and find it. Okay.
Ma'am, can we do the revision quickly? Like, if we want to check 1 1, what we have to do? Like,
Yeah. 1 1 means, what is 1 1 definition?
1 to 1, like there is for each element in X in the domain, there is a one single element in the
Yeah, if
mapping.
some function is there, f of x1 equal to f of x2
Yeah.
implies x1 equal to x2, right?
Mm-hmm.
If this condition is there, we will say 1 1. Okay. Now, what is d of 1?
D of 1 is 0.
0. What is d of 2?
D of 2 is 1.
D of 2,
Sorry.
what is the function here? Function is constant function 2, right?
Okay.
That means derivative of the constant function. Derivative of any constant function. Whatever c I am taking, derivative will be 0, right?
Okay. Okay.
Now, it
Mm-hmm.
is not 1 1. This implies not 1 1, right?
Mm-hmm. Okay.
Okay. Now, uh, can you find any function p of x such that d of p of x equal to x cube, with the degree of p of x is always less than or equal to 3. Correct? P of x coming from v. P means degree less than or equal to 3. Now, if I am, what will be this p dash x? Okay? If p of x has degree less than 3, what will be degree of p dash x? 1 degree reducing. We are taking the derivative.
Mhm.
Okay? If we are taking x cube, it will become 3x square. If you are taking x power 4, then only it will become some x cube term. Okay, but we have in v up to x cube term only. So degree of p dash x will be less than or equal to 2. Since p of x has maximum degree 3, its derivative will have maximum degree 2. So the third degree polynomial we cannot have. Okay, so it is not onto. Are you getting?
No, I'm trying to understand. So for onto, we are taking onto means like for all the elements are covered, but you are saying that here, since x square is not covered,
Not x square, x cube.
x cube is not covered, so it is not onto,
Yeah,
right?
yeah. For
Okay.
example, if I am taking a naught plus, this is
Mm-hmm.
the general form.
Okay.
Okay,
Yeah.
now d of p of x will be a1 plus 2a2x plus 3a3x square. I cannot write it as some x cube, right? Because x cube has high degree 3. Like with lower degree, I cannot write it a x cube.
Mm-hmm.
Okay, so x cube is like no function is mapped to x cube under the map D. So it is not
Mm-hmm.
onto.
Okay. Okay. Fine.
Okay, so that's all. Okay, then this is our last class. We can stop today, right? Any other doubt? Anyone?
Ma'am, regarding exam,
Hmm.
uh, I got the hall ticket and everything
Yeah.
today,
Yeah.
and it's going to be a 3 hour exam. They have mentioned in the ticket, but
Okay.
um, but the format and all is not given. It's not even there on the internet anywhere. If you guys like, if you have seen previous year's papers, can you give us some hint, like what kind of?
No, regarding exam, I don't have any idea actually, but it is computer-based exam, right? Online.
Yeah, it is online
Yeah, so
only.
it will be objective only mostly. Like maybe multiple select question or multiple choice question, both can be
Okay.
there. Uh,
Mhm.
yeah, nothing like descriptive question. It will not be there, I think. So if you have, maybe you can ask in the forum, right? In that portal,
Yeah,
you can.
no response is coming.
Yeah, this regarding exam and all, we don't know actually.
Okay.
Yeah, mostly it will be this kind of things like whatever you are doing assignment, those kind of question. Like
Okay.
you have to apply the concept whatever you have studied, but it
Hmm.
will be like multiple select or multiple choice.
Hmm.
Yeah.
So on the Saturday it is there. Yeah.
Okay, this coming Saturday.
Yes, yes.
Okay. Yeah, then all the best for the exam. Do well.
Yeah, thank
Okay.
you.
Yeah.
Thank you,
Okay,
ma'am.
then let us stop. Bye. Thank you, everyone.
Yeah, thank you, ma'am,
Yeah.
for your coaching. Very
Oh,
good
okay. Yeah. Good
session.
night.
Thank you.
Yeah.
Bye.
Thank
Yeah.
you,
Bye.
ma'am.
Bye.
Thank you so much.
Yeah. Bye. Good night.